Okay, so Tendermint is a consensus engine. So Tendermint, we're building a distributed system. So that distributed system is going to have multiple nodes. And if what we're doing is another layer of complexity, but if we just look at a single Tendermint chain or Tendermint system, there are multiple nodes. It's a distributed system. Those can exist across multiple different servers and countries, and it's a distributed system. So since everybody is processing the same set of transactions, and everybody, all the nodes need to agree. So Tendermint primarily is a system that that facilitates that consensus building between the different nodes to ensure that all of the participants in the network come to the same conclusion when they're processing transactions. And Tendermint does some other stuff in line with that, like making sure that the transactions are all processed in a specific order. So the machinery of Tendermint, when users are submitting transactions and Tendermint is deciding how to process those, part of that involves putting them into order. So there's a lot of stuff that we get from Tendermint, but its main role is consensus. And Tendermint defines what they call an application blockchain interface, because Tendermint does not care what your data looks like. It is totally irrelevant to Tendermint what the actual application is doing. What you can use Tendermint for anything within some constraints. So the transactions, from Tendermint's perspective, are blobs. They're just chunks of binary data, and it has no idea what a transaction means. And so when working with Tendermint, you have to define an application, or you have to have an app. You have your application that does whatever it is that you need it to do. In our case, the application processes the accumulate transactions. So the ABCI is the interface in between Tendermint and your application. And if you are writing your application in a language other than Go, if you're writing it in JavaScript or Python or Java or whatever, there is a protocol buffer or JSON RPC based interface between the two, so that Tendermint you can run your application as a separate executable, and Tendermint can communicate with it. And in that kind of architecture where the application is running separately, the ABCI is the request response interface between the application, between the internal state machine and Tendermint. And if we look at the actual the interface definition, so Tendermint defines the application interface, and these are all the methods. And these 5 methods are the primary interface for transactions for the consensus system. There's some state management stuff, and info is required for some of the keeping track of certain things, and query is defined by the application. Query is just passed through. But these 5 here under consensus connection are the main ones. And if we look at commit, the commit response includes data, and in other places data is called app state. So when I say consensus, what that means, among other things, is that when a block of transactions are committed, everybody must agree on what the app state is, or what the data result in the response commit is. So in our case, it even says Merkle root hash. Okay. So the Tendermint is saying here that the I assume that what they're saying is that the data is going to be the app state is going to be the Merkle root hash. And in our case, it is the root of the Patricia tree. So it's a hash tree root. The details are a little bit different because of how we're using the Patricia tree. But the point is that the app state is the root of a hash tree that includes the entire state of the system. So all of the nodes must agree on the final app state. And this, the way this works is when users are submitting transactions, they get checked to make sure that do some validity checks to make sure that we're not flooding the system with invalid garbage transactions. And once a transaction passes through check, then Tendermint decides what order it's going to be processed in, and it starts a block, delivers all of the individual transactions, ends the block, and commits. And so for every node, deliver will happen in the same order. So no matter where a transaction, no matter which node the user sends a transaction to, Tendermint will figure it out and decide what order to execute them in. And then they all get executed in the same order, and then they all need to produce the same root hash. So that's the role of Tendermint. It's this consensus system that means there's a lot of stuff that we just don't have to care about. Like, we won't get identical transactions because if a byte for byte identical transaction, and again, transactions are just bytes. Tendermint doesn't have any idea what any of this is. Oh, that's the response type. Tendermint doesn't know what any of this data is. It just thinks it just says, here's your chunk of bytes, do what you want with it. So if somebody delivers an identical chunk of bytes, Tendermint will say, hey, I already saw that. I'm going to reject it because we already got that transaction. And it ensures ordering, and there's a consensus. So that is the role of Tendermint. Now, from the accumulate side, we can look at accumulate from from different perspectives, from different design point of views. When we say the protocol, we're talking in very abstract terms and thinking about the system as this ideal abstraction. The protocol has records and transactions. And we have light token account. Well, for the most part, we have the identities, the ADIs, and almost everything belongs to an ADI. And as we add more records, I think everything else that we might add is going to be added as a record under the ADI. The only exceptions are the light token accounts, and this should read light data chain. So the light data chain and the light token account, those are the only things that do not belong to an ADI. So, okay, sorry, to go back, this idealized architectural model of accumulate, you have these different records, and each record has a URL, and then there's transactions that you execute against the record. And, it behaves in some ways like a typical web application where you have a database and the database has records, and then you have actions that you can take that manipulate records in the database. And we have transactions that you can execute that manipulate records in the database. So from the 1,000-mile high perspective, our system has those characteristics. We have that database with records, and we have these transactions. And we have these types of transactions. Everything has a URL. All records have some URL associated with them. And we have the light token account, where the URL is based on the public key hash and the token issuer, like Acme. So the light token account has no identifying information beyond the key hash and is not associated with anything else. So it's kind of off and independent. It's like a typical blockchain account where you have a key and that's it. So light token accounts map fairly well to typical blockchain accounts. Light data accounts are a bit more special, a bit different. They are also identified solely by a hash, except it's not a hash of a key, it's a hash of some fields, some binary fields. And the light data accounts don't have any keys and can be written to by anyone, by any transaction with a valid signature and a valid key, which means you have to be doing it with like a light token account or an ADI or something like that, can write to a data account. Data accounts map to Factom, and they're part of our Factom migration. But they can also be used. They're kind of like, I think of them kind of like wiki pages. Beyond that, everything belongs to an ADI. So we have a base identity, and then you can have token accounts within that, and you can create your own types of tokens. I could create Ethan tokens if I wanted, and I can issue my own type of tokens. And then you have key management structures, the key book, which contains key pages, and an ADI can have multiple key books, and we can go into that more, but those are the key management structures. And then there's the data accounts, and then beyond. And data accounts, those are a data account or data chain associated with an ADI. And we have more restrictions on who can write to those, and those have not been implemented. So I'm not going to talk in detail about any restrictions or anything like that until we've actually figured that out. And just because I like to jump around all over the place, let's talk a little bit about URLs. Mostly, we are not using any of the user info. So our URLs pretty much are just authority and path. And this, like here it says authority because that is what the URL specification refers to it as. So from the perspective of the rest of the world, the host name and port number or domain name or IP address, that is the authority. For accumulate, the authority maps to the identity. So for an ADI, the identity is, or for an ADI or a record within an ADI, the identity is whatever you want it to be. So for a light token count, the identity is derived from the key. And, it's not just the key. You take the hash of the key, and then you take the hash of the hash, and that's a checksum, and then you put those together. But point is, it's a hash derived from the public key. And then you have the token issuer. So those are URLs. And transactions, I'm not going to go into detail, but we have a variety of transactions. You can create identities, create token accounts, etc. And okay, well, before I talk about synthetic transactions, so if you've read the white paper, you'll be familiar with this, but I think we have people here who have not read much of that. This is not where I wanted to go. Or the light paper. So the light paper talks about accumulators and validators. So we're now referring to these as block validator networks and the directory network, because the chain is a bit confusing. But the point is that the majority of transactions, user transactions against ADIs and token accounts and light token accounts and all this kind of stuff, these are processed by the BVNs, by the block validator network or networks. And we potentially have multiple block validator networks. So, we have accumulate so this is talking about the architecture of accumulate from the network perspective, from the perspective of the network operator, or, if you're developers thinking about how does this system, from an engineering perspective, how does the system actually work? And one of the differentiators is we have the block validator networks, and we intend to have many block validator networks. So you have individual chains to clarify, we talk about chains in the context of accumulate. Chain means Merkle tree. We don't have any, we do not use typical blockchains, typical linear chains with a block that has a parent hash, and then the next block, the hash from that block goes into the next block as a parent hash. We don't have linear chains like that. We exclusively use Merkle trees. But in terms of how we can use them, Merkle trees serve the same purpose of being a chain of transactions, a linear history of transactions. Just the data structure is a Merkle tree. So something to be aware of, chain means Merkle tree. Each individual record is effectively a sidechain. So each individual ADI, each token account, each one of these things individually has its own chain. And they are more or less side chains. And those chains get fed into the anchor chain for the BVN. And then we have multiple BVNs, and those anchor chains for the BVNs get funneled into the directory network. So we have multiple chains, multiple side chains. Everything is effectively a side chain of the directory anchor chain, and then the BVNs have their own anchor chains that tie into that one, and then all the records tie into that one. So we've got this tree structure of trees. Block validator networks matter. Well, having multiple block validator networks matters because what we're doing is we're looking at the URL and we are routing transactions to a specific BVN dependent on the URL, which means that we can, as we need to scale, if a particular BVN gets overloaded, if it's receiving more traffic than that network can handle, then we can split that BVN in two, or three, or however many we want, and change the routing to balance the load across the BVNs. Now, this is not a typical load balancer, because in a typical load balancer, any of your instances can handle any of the traffic, so the load balancer can put things wherever it wants. It's, in a sense, load balancing, but it's a more static process. So, we have multiple BVNs, and records get routed to those BVNs based on the URL. And in, I think, in one of the next releases, we will be working on a routing on ADI routing locations, ARLs, and a mapping table that maps from ranges of ARLs to BVNs. And one way this could work, we haven't worked out all the details, but one way it could work is something like net masks or subnet mask with IP addresses, where you have a certain number of bits that are considered the network portion and some bits that are the host portion. So we could have masks where some part, the first 5 bits or the first 10 bits of the ARL, or of the routing number, let's just say routing number. So the first 10 bits of the routing number map to some map to a BVN, and that can be variable, and we can get fancy with that. But the point being that we can have a routing table that will map ranges of identities to BVNs. And as we need, we can intelligently split things, and we can intelligently split the BVNs, which means we should be able to scale linearly. So as the amount of traffic on the system increases, we should be able to just keep on fracturing the BVNs and creating more and more and more BVNs. And the system should hopefully indefinitely scale linearly horizontally linearly, as in we are creating, we're splitting up the BVNs into more and more BVNs. And so on this level of the diagram, more or less, it's getting wider. And that should allow us to reach very high TPS numbers and total load, because each individual BVN, as we, if we split up a BVN, the records that BVN is required to keep will be able to each BVN will only need to keep the records for the things that are routing to it. And that's a point that I kind of glossed over. So let's talk a little bit about the URLs again. So, we have the URL, and there's the authority and the path, and that's primarily all we're caring about, or the identity and the path. The identity being more or less the host name, and the path being everything after that. And we have the notion of the identity chain, or chain ID, which is a hash. And that is calculated purely from the first part, from the identity or host name. And then we have the resource chain, which is calculated from both. So the resource chain is where things are stored in the database. That's not an important detail. So for routing, we take the hash of the identity, the hash of the host name, interpret the first 8 bytes of it as a integer, and that is our routing number. So anything belonging to a given ADI, to a given identity, will get routed to has the same routing number, since the routing number is based on that identity. So, when I was talking about ARLs or routing numbers, we're looking at the routing number is the first 8 bytes of the hash of the identity interpreted as an integer. Because this is a SHA-256 hash, those should be effectively normally distributed, a flat distribution across the space, the number space of a 8-bit or 8-byte integer. And then we can use, we should be able to use any bits. And right now we're doing some very simplistic routing with modulo math, but with the routing table, we'll have the first 2 bytes or bits, or the first 3 bits or whatever, are routed to some BVN, or it will be something like, if the first 3 bits are 0, 1, 1, then route it to this BVN. If the first 3 bits are 1, 0, 1, then route it to another BVN. And if the first single bit is 1, then route it to this, etc. So we can have a flexible routing system. But with that routing, the BVN must have, any given BVN must have all of the records it needs in order to validate a transaction submitted to that BVN. So if I am doing key, if I'm adding or removing a key from a key page in an ADI, all the record for that key page needs to be held by the BVN that transaction is routing to. Or if I'm doing anything in an ADI, then the BVN needs to validate that the key I'm using is the correct key, and that key is authorized to manipulate records in the ADI or whatever I'm manipulating. And so the key book and key page that holds those keys for whatever, for the token account that I'm sending tokens as, or for the data account, the ADI data account that I'm writing data to, whatever key book is governing that record, all of those records need to be in the same place so that the BVN can validate it. However, there's a complication there, in that if I'm doing things, if the user submits a transaction that interacts with records in different, that belong to different identities. So if I send tokens from an account in my ADI to an account in Paul's ADI, I should always assume that two different identities will get routed to different BVNs. So when I send tokens, that transaction will be routed to the ADI, or to the BVN that my ADI gets routed to. That ADI or that BVN likely will not have all of the not have records for Paul's accounts. So we need to be able to execute transactions that span BVNs, and that's the purpose of the synthetic transactions. So the synthetic transactions, whenever the user submits a transaction that will interact with records on a BVN other than the one that may, whenever the user sends a transaction that has the potential of interacting with records that belong to an AD or that are routed to a BVN other than the one that the transaction is routed to. We need a synthetic transaction for the second half of that. So concrete example, sending tokens. If I send tokens from my account, that transaction will get routed to the BVN that my account gets routed to, that my identity gets routed to. And in order to deposit the tokens into Paul's account, that has to be processed on the BVN that holds the records for his account. And so the token send transaction, the token exchange, produces a synthetic transaction. And that synthetic transaction is routed to the BVN that Paul's account is routed to. So you say, I want to send tokens, that goes to BVN1, and then BVN1 says, okay, well, you're sending tokens to this other account on this other BVN, so I'm going to generate a synthetic transaction, that goes to BVN2. So in effect, you have a withdrawal tokens and you have deposit tokens. So the withdrawal happens on your BVN, more or less, the one that your account, your identity, that the sender's identity is routed to, and the deposit happens on the ADI or on the BVN that the recipient's identity is routed to. And there's a variety of situations where this kind of thing happens, and we have a variety of synthetic transactions, but that is the network infrastructure. Anybody have questions? Anybody hopelessly confused at this point?
I just asked how validators are assigned to each BVN.
As in, if you want to join the network as a validator and set up your own node, how do you get assigned to a BVN?
Yep.
Hasn't been decided.
Okay.
Oh, Actum, yes. When I say everybody, I mean 2/3 majority. My assumption, my assumption is that the system will, in steady state, the system will be operating. Everybody, all the validators will be working correctly, and so all the validators will be agreeing. But yes, for a transaction to go through, 2/3 of the validators must agree. So Tendermint, the consensus system of Tendermint, it is Byzantine fault tolerant, so there's many different error conditions that it can handle. So yeah, you don't need 100% consensus. You need a 2/3 majority. If a particular validator node consistently fails to arrive at consensus, it will be kicked out of the network and its stake will be slashed. Okay, so next item on the agenda, talking about the overall tech stack. Now, I did not prepare slides, so for now, we're just gonna look at code. So there's Tendermint is the consensus layer, and that's not code that we're writing. Tendermint, we have some code to initialize and configure Tendermint and boot it up when the application starts, but that that's housekeeping. The bulk, the consensus engine, that's something that we're pulling in as a dependency, not something we're implementing ourselves. Inside of Tendermint, we have the ABCI application implementation. So we have our implementation of the Tendermint state machine. And again, the important parts are primarily, or the most important, the parts that are important for processing transactions are those 5 methods I highlighted earlier. We have these 5 here, and a init chain is only called on the first boot. So init chain is, we have a Genesis state, and right now that's just a few records. In the future, that will include factums data. And so there's a init chain, just gets everything started and loads the Genesis state, the Genesis block, and populates some of the initial records like the Acme token issuer and the Faucet token account. For normal processing, we have begin block and end block, which don't do well. Actually, the begin block now does some things. So there's some work we do at begin block, and then check is the validation. Anyways, okay. So talking about our tech stack, this is the ABCI application implementation. This is the entry point to our system from Tendermint's perspective. So in terms of what Tendermint is aware of, we provide, to clarify or to rewind a little bit, you can have a different process, one process for the application and one process for the Tendermint node, and they communicate over TCP or a Unix socket, through the JSON RPC or gRPC or something like that. Because we are writing our system in Go, we don't need to do any of that. So we're writing this in Go, and that allows us to implement just a Go interface. So we implement this application interface. We don't have to have any TCP calls between Tendermint and the ABCI. And somewhere in here, we create an application, and then that gets passed into Tendermint. So this is what creates the Tendermint node, and we just hand it an instance of this object, and that implements the application. So from Tendermint's perspective, this is the call. Well, that's the call that initializes it, and somewhere down here we say node.start or node.service.start. But anyways, so this is creating the node, and down there somewhere in this file we're starting the node, and that's all Tendermint knows about. And so that creates the Tendermint layer, and then there's the application. Additionally, on the outside of Tendermint, we have our API. So I'm going to go through API v2. API v1 is basically the same idea, but it's a bit more complicated to track through how everything happens. So on the simpler side, on API v2, so we have a JSON RPC API, and we might expand that to WebSockets or gRPC or whatever. But right now, all we have is this JSON RPC API. And it defines a variety of methods. And if we look at one of the simple ones, query, there's some extra processing here, but at some point in time, that is going to be calling into the query dispatcher. And the query dispatcher, right now this is doing the simple modulo-based routing. It's not very complicated routing, but this is the early routing implementation, just because we need something. The final mainnet routing will be a routing table, and will be much more configurable and have less awkward implications than just directly saying, how many networks do we have? Take the routing number modulo that many networks. But this is the query dispatcher. So, so the API is a layer on top of Tendermint, and we can trace this through, and there's a few layers here, but eventually we're making a call to into Tendermint, and that's how it's working today. It's not necessarily how it has to be for the query, but if you trace through the calls, we hit query or ABCI query, and that goes through Tendermint. So we have this layer on top, and that's querying into Tendermint. And same thing on the transaction side. It's more complicated for the transactions because these are getting batched. So the transactions get packaged up with the current settings when a transaction is received, either the next 100 transactions or for the next tenth of a second or something. All the transactions are packaged up and rolled up into a batch. So this is complicated because of the batching, but one way or another, the transaction will be routed to the BVN that is responsible for executing it. And this is the batching. We've got the batching going on here, and the batching and the dispatching, as in rolling up multiple transactions into a batch and sending that batch to the appropriate BVN based on routing, is handled in the API. So this, for API v2, for executing transactions, the routing is handled in this file, in these methods, and eventually that call is sent, and that will be sent to the BVN that will be executing it locally. And then, we construct the transaction, turn it into bytes, and there's a parameter for only run check. But unless you do that, then we broadcast it. So here we're calling it the Tendermint. So our tech stack, we have this API, and the API sits on top of Tendermint and sends requests to Tendermint, executes transactions going through Tendermint. And then inside of Tendermint, so to speak, there's the ABCI implementation. There's the application or the state machine that executes transactions. Now, in terms of how we're actually executing transactions, once the transaction gets broadcast, and users can broadcast directly, we will have code in the future that will reject transactions if they end up going to the wrong BVN, and they will probably fail anyways, because if you manually broadcast a transaction to a BVN that doesn't have your records, it's not going to find things and it's going to fail. So once a transaction gets broadcast to Tendermint, this function, deep somewhere down in the code, Tendermint has many layers of code. That ends up calling check.tx and deliver tx. And there's a begin call before transactions are checked asynchronously, more or less. And when a transaction is valid, Tendermint, puts it in a queue or something. I haven't dug into exactly how Tendermint works. And then once Tendermint has decided what transactions are going to be executed in the next block, it calls begin block and then delivers all the transactions, then calls end block. In terms of executing transactions, the broadcast call through this process, and it's not direct, and there's channels and loops and queues and all kinds of, if you try to debug through Tendermint, there's a ton of layers. It can be pretty daunting. But eventually, that transaction, whatever transaction gets broadcasted here, this chunk of bytes makes it in here, and this has a TX property that's just bytes. So it goes into deliver. And there's some stuff in here, unmarshalling and getting a hash so we can do some logging and whatnot. But primarily, the chain executor or the transaction executor is doing all the logic. So ABCI, the accumulator, the ABCI implementation is mostly a translation layer between Tendermint and how our internal system works. So most of the actual logic is in the chain transaction executor. Now, that might change as we handle adding validators, because part of what this code does, part of what the application is responsible for, is handling validator updates. And when a new validator node attempts to join the system, determining whether or not it should be allowed to join and things like that. So this might get more logic on that end. But right now, it's primarily a translation layer, and almost all the transaction processing happens in the executor in the chain package. And the original architecture talks about chain validators. The chain, you can think of the code in here as chain validators. It's a bit more clear to think of it as transaction executors, the things that are responsible for executing transactions. It's originally, Paul intended for this to be built around chains and to be focusing on looking at chains. But the way that Dennis and I built this, it's focused on transactions more. So I think Paul's vision, there was going to be a chain validator for identities and a chain validator for token accounts, but we actually have a transaction validator for the different kinds of we have a transaction validator for create identity, and we have a transaction validator for send tokens, etc. But they're also executing, so think about it whatever way makes sense to you, but the point is this is executing transactions. So in here, we have begin block, and begin block does housekeeping and manages the details of synthetic transactions, so I'm not going to go into that right now. Mostly for this discussion, begin block tracks the number of received, or the number of the number of blocks that Tendermint has created. So Tendermint creates a block roughly every second with the current settings. So it receives transactions and it goes through its process and figures out how it's going to, if those transactions are valid, does the check TX and decides if it's going to execute them. And then once Tendermint decides here is the set of transactions that I'm going to execute, it starts a block. It says begin block, executes the transaction, end block, and that is a Tendermint block. And every time it does that, the Tendermint height, the number of Tendermint blocks, increases by 1. So if we look at the transaction log, you'll see height 1, height 2, height 3 as time goes on. And those blocks happen roughly once a second. It's not exact, but that's the timeout that's set. So in here, the meat of the code is, well, we'll talk about CheckTX first. CheckTX is a simpler version. Mostly it calls, so this is doing checks that apply to everything. So just make sure the signatures are valid, and we'll look at that a bit, but make sure all the signatures are valid, and then get the transaction executor for the specific type of transaction. So we can look at transaction types, and we have a code defined for each transaction that should match what's in that markdown file. And we define executors for the various different types of transactions. And so check, once it does the basic checks for signatures and stuff like that, it looks up the specific executor in a map. And, this could also be a switch statement, possibly. And then it calls validate on the transaction executor. And each transaction executor, has its own implementation of validate. If we're creating an identity, then, unmarshal the payload and make sure that the URL, so when you're creating identity, you say what, if I want to create Ethan, then the URL is Ethan. And this, check that it's valid, make sure that it's okay to be an ADI, because there are certain things that you can't have as an ADI URL, etc. So each transaction type has its own logic. And so that's check. And then in deliver, we have additional logic because we're actually going to be processing the transaction and saving things to the database. And so there's more stuff we need to do here. But we still have this core, check the signature and whatnot, and then execute the transaction. And then there's more stuff to save things into the database and record the transaction and commit the state changes, because there's only one method. The transaction validators, or the individual transaction executors, only have a single method. Well, except for that one. But in terms of doing things, in terms of executing things, they only have validate. And this will add the state records to the list of things that needs to be committed to the database. In the case of check, that all gets discarded. So you can do whatever you want with the state manager, but if commit is never called, those changes will never go anywhere and they'll be discarded. So in deliver, we call commit.
Hey, Ethan, a quick question here, just on that ADI check. What it precisely is being checked for when you're checking the validity of an ADI?
Of the URL or just in general?
Well, I guess both. I was particularly interested.
You were particularly looking for what?
Interested in the URL, yeah.
Has to be UTF-8. Can't have a port number, so I can't do Ethan :123. Has to have an identity. Can't just do /foobar. Because we want to handle domains in some other way, possibly with a domain registrar, identities cannot currently contain dots. And it has to be something more than just a number. I can't create 123 as an ADI. And it needs to not be a 48-character hexadecimal sequence. So this check makes sure that you can't try to do weird things where you make an ADI that looks like a token account or a light token account. ADIs cannot currently have a path, so I can't create Ethan/car. The query portion of the URL, so !, search equals whatever, can't do that. Fragment, which is the hash mark, so when you click on a anchor in the page and you get a hash something at the end of the URL, you can't have that. And then it checks for Unicode. So this is what constitutes a valid, beyond what is a valid accumulate URL. This is what determines what is allowed for an ADI. And I think we have tests here, so this lays it out in a bit clearer language, and we should probably write some of this down somewhere in a document. But that's the code that determines if it's a valid URL.
Got it. Thanks.
Okay, so we have talking about the tech stack for our system internally. There's the ABCI implementation that calls into the executor, and then the main executor calls into one of the individual per transaction executors. And then that is doing various that's calling various StateDB methods like add transaction and add state entry, etc. And then so we can look, I'm not going to talk about this in detail, but just in terms of how data gets into the database. Oh, I have a diagram. So this is, glitchy. What are you doing, GitLab? Okay, that's better. This is slightly wrong. Check TX happens outside of the block. But this doesn't really tell you anything. Well, anyways, you have, transactions come into Tendermint, and then that calls into the ABCI, and that calls into the executor and the main executor and the transaction executor, and then this doesn't tell us a whole lot. Okay, so we have StateDB, and there's a variety of methods in StateDB, and this is the executors primarily interact. So if we look at the individual transaction executors, they do things like call create on the state manager, and that adds it to some data structures. So the state manager has a variety of data structures, and while in the body of the validate method, records and whatnot changes are added into these maps and arrays. And then on commit, those changes are pushed into the database or into the database transaction. Update nonce. We have, okay, there we go. Add state entry. This is writing updating, like a balance on a token account or something like that. So this is going into StateDB, and then this is, again, going into some data structure somewhere. And during commit, so the accumulator calls commit, well, Tendermint calls commit. That passes the message to the executor. That passes the message to StateDB. StateDB does commit, and this is writing data out to the database through SMT, through the stateful Merkle tree library. Change state. So we're adding records into the Merkle tree and writing things out to the Patricia tree and writing records out to the key value database. And then this, this is going into the database manager, which is writing things out to one of the key value implementations. There's Badger and an in-memory database. And so, that is the flow of data into the database. And we have the ABCI calling into the main executor, calling into the transaction-specific executor, and queuing up writes. And then when that transaction passes, those get committed, which queues up writes in this layer. And then when the block finishes, when the Tendermint block is committed, then those writes get pushed out into the database. And some of them get written directly, and some of them go through the Merkle tree logic. All right, so that's, rough overview of the whole tech stack. Now I'm going to dive into debugging and really getting into the nitty-gritty, stepping through the code.